Hi, this is Doug Sparks from M2M Technologies, and today I'm going to talk about transition metals and silicon, the contamination issues, rapid diffusion, and then a variety of device problems that have been seen with these elements in silicon integrated circuits and sensors. Now, most BiCMOS front-end fabs forbid the use of transition metals as layers, as metallic layers. They're basically restricted to the back-end fabs. Transition metals were noted in the 1960s to cause emitter-collector pipes and bipolar transistors, diode leakage, low minority carrier lifetime, and then in the area of the CMOS devices, we saw them causing gate oxide defects. So there's a lot of problems with transition metals, and a lot of techniques have been used to avoid contaminating silicon wafers and to clean silicon wafers. Now, when you're talking about many new devices, there is a desire to use a variety of transition metals in either in metallic or oxide form. For example, MEMS devices, FinFETs, getters for vacuum packaging, etc. So there is a need for these metals, but you've got to be cautious in implementing them into your process and design. One of the things that a project I worked on, we looked at using silicides in single crystal silicon structures using epitaxy. We found that if there were silicides on the starting wafer or even embedded in the starting wafer, they would diffuse through the wafer, form precipitates on the surface, which would cause epitaxial defects. And this is a photograph from several years ago of some palladium-related stacking faults and defects caused by these buried transition metal runners. Of course, silicon epitaxy is done at, say, 1,000 to 1,200 degrees C with various dichlorosilane or trichlorosilane compounds. But we quickly learned that we couldn't use transition metals at these high temperatures. Today, in advanced nodes, we've been using copper, tungsten pillars, moly, a variety of like hafnium, a variety of different types of transition metals in the back-end fab for interconnects, metallization, stack-ups. And as I mentioned, MEMS devices also use a variety of fast diffusing transition metals as well. And these are traditionally MEMS devices are fabricated in foundries that have no CMOS or bipolar devices, so there's no worry of having these materials in active circuit devices, or in the case of your typical foundries, a CMOS foundry, they would be in a back-end process where they would see no high temperature applied to the silicon wafer itself after the deposition of these films. Now, where does metal contamination come from? And we found this in older BiCMOS and bipolar fabs. It basically came from the stainless steel tubing or wafer fab processing equipment. For example, in one case I was involved with, we transferred a used epitaxial system to a new fab, and chlorine compounds in the stainless steel tubings formed iron chloride and nickel chloride compounds, which contaminated wafers that were processed on that piece of equipment after it was reinstalled in the new fab. So these were corrosion byproducts. So that's one common thing. We found that just running wafers on belts and chucks that may have stainless steel particles, they'll transfer on the back side of the wafer just via scratching and can rapidly diffuse through the wafer during the first high temperature thermal cycle. So it was there was a lot of work done in the equipment industry to avoid contacting silicon with stainless steel. There were also a number of really interesting and very functional cleans, the most famous of which is called the RCA clean, and it can clear away alkali metals that cause CMOS gate issues, as well as transition metals, which would cause these emitter-collector pipes or diode leakage. And I encourage you to dig into that, but typically these solutions are like a sodium, ammonia hydroxide, hydrogen peroxide, hot liquid that'll do some thermal oxidation of the surface, which will trap the metals in the oxide surface layer, almost like a native oxide surface layer, and then a subsequent HF step will etch that away and clean any residual transition metal or alkali metals off the surface of the wafer. And that's a very effective technique for getting incidental contact, like a scratch or some sort of particle from contaminating a wafer during a high temperature step. And so this is usually done before epi deposition, furnace processing, etc. Now, how do you detect metal contamination? We've used a variety of techniques. If the wafers are already processed, we often used a defect etch. Depending on the orientation of the wafer, sertal and right etches, you could see these precipitates will form at the surface where they nucleate. We often call them S-pits. You could see those, this white haze on a wafer. You could use KEVX, secondary and ion mass spectroscopy. If you want to send samples out, you can do neutron activation analysis. If you have wafers, you can usually hit those with infrared or some sort of deep level transient spectroscopy technique. So there's a variety of methods used and developed to look at contamination. Now, it was really an interesting thing I observed when rapid thermal annealing first came out, was that you could scratch a metal on the backside of a wafer, take, say, a stainless steel tweezer. You could anneal it for 30 seconds at temperatures of like 800, 700, 1000 degrees C, which we used for ion implant activation. Do the defect etch, and the pattern, the S-pits or the haze, would be on the opposite side of the wafer. So these metals were diffusing through the entire thickness of a wafer, over 500 microns in less than 30 seconds. So that was a really remarkable observation. We had all thought previously that transition metals are fairly large and they diffuse substitutionally, which would just, would only diffuse a few microns in hours. But we found that a certain percentage of these transition metals diffused interstitially and can actually move through an entire wafer pretty quick. So this just kind of illustrates substitutional versus interstitial, which is fast diffusion. And here's some data. This is a paper I wrote a number of years ago, just comparing the different detection techniques, which metals could diffuse through a wafer in 30 seconds at different temperatures with different silicon wafer orientation. And basically all of these metals would diffuse through a wafer by almost every detection technique we tried in the 1000 to 1100 degrees C temperature range in just 30 seconds. Some would diffuse through at 800 degrees C, and I remember nickel was the one metal that would diffuse through in 500 to 600 degrees C. So very rapid diffusion. So if you do get a contaminated wafer, it's going to spread everywhere. Now, one way, once your wafer is contaminated and it's been heated, there's only one way to get the metals out of the active surface region of the wafer, and that is through gettering. And so gettering means trapping. So you're trapping the transition metals at defects like dislocations or precipitates or surfaces. And luckily they move fast, so they can move and get attracted via the stress gradients in the material and get trapped in these areas. For CZ silicon, there's a lot of oxygen in there, which will precipitate after a high temperature long anneal, and you can basically use those silicon oxygen precipitates in the center of the wafer to trap the transition metals and allow you to make functional devices on the top surfaces. And from a microfluidic note, these oxygen transition precipitates that form in ZZ wafers can sometimes survive a plasma or wet etch, and then you have these little 10 to 15 micron precipitates rattling around in your fluidic channels and clogging things up. So that's something, if you're working in microfluidics, it's another failure mode, is transition metal related precipitates. Okay, just a summary of transition metals in silicon. They can degrade a variety of bipolar and CMOS devices, from PN junctions to gate oxides. You've got to avoid transition metals at all costs. Don't process transition metals on wafers at temperatures greater than 500 degrees C, or they're going to diffuse in rapidly into the silicon. And as I mentioned, they can diffuse hundreds of microns above, say, 500 to 700 degrees C in just a minute. You should make all efforts to clean any metal residue off the surface of the wafers. But once they're in the bulk, you've got to go with a gettering approach, which involves internally or backside surface located damage sites to attract these metal atoms and precipitate there or getter there. Thank you.